Okay, this video we go over the Simul8 homework solutions. There's 3 problems. I went ahead and modeled all 3 problems in the same file. You did not have to do that. You could have submitted 3 files. Most of you did. I think maybe all of you did. But you don't have to. The key is that on the time periods, the results collection time period, I'm just using a non-specific daytime period and a simple count. And so each of these are run separately. You just have to interpret it in how you inputted the data. So we've got it's 3 different problems all in the same file. The first problem is this ATM. And in that case, I've got people showing up every other. They show up every other minute, and then it takes a minute and a half on average to process with a 10-second standard deviation on the processing time. So people are showing up. I modeled the first one in seconds. So the time between is 120 seconds. It's exponential. The service time is 90 seconds with standard deviation of 10, and I made it normal. I've got to collect the statistics we need to collect are the average time in system, the probability that a customer will not have to wait, and the average number waiting to use the machine. So let's look at part B specifically. How do I get the probability that a customer will not have to wait? That is going to be calculated from the ATM. If I look at the results, the awaiting work is equivalent. That's from a machine's perspective. It's the probability that the machine is idle. The probability that that particular ATM is not being used. So from a machine's perspective, that's what it is. From a customer's perspective, if the ATM is idle, then that is the probability that you don't have to wait in line because there's no one there. So that awaiting work percentage will answer that. For the second problem, it's this dock, and we're trying to optimize our cost, and so it's a trade-off of adding capacity with the cost of that against the cost of people waiting. So we have those costs, but notice what I did. I modeled a scenario with 1 dock. I also modeled another scenario with 2 docks, and then another scenario with 3 docks. But how did I do this with just 1 entry point? Look what happens. I've got people showing up. The rate is 5 per day, so the time between arrival is 1/5 of a day. So my unit of measure for this problem is days. But look what I did. I batched out 3 things, and then I routed out using a circulate. So the first one will go there, the second one will go here, the third one will go here. Let me move that over. The first one will go there, the second one will go there, the third one. So every time a truck arrives, it gets cloned and then we actually have 3 trucks arriving at 3 different systems I'm trying to evaluate, but it's an apples to apples comparison because the arrivals all occur at the same time. You didn't have to do that, but that's kind of a cool way when you're trying to model system design choices. The service time for all of my docks are also 1/5 of a day with an exponential distribution. And then the last one, we have things arriving. So I've got a rate. So the very first one, they show up 1 per day. So I put that in the denominator to be consistent. The next one's, the arrival is per hour. So the second one is if they show up 2 per hour, then the time between arrivals is 1/2. I think that's how it works. Yeah. So the priority 4 people show up 4 per hour. So the lowest priority, they show up most often. Yes, so they show up every 1/4 of an hour. Now, when they show up, for all of these, I have a label I've created. under actions or label actions depending on the version of Excel. And so for this last one, that label is set to 4. And then on my servers, all of my servers, when I route, well, first of all, it's a normal distribution. I can do 3 per day, so the time between arrivals, or time between service, the service time is 1/3 of an hour, and a standard deviation is 5/60ths of an hour. I route out based on my label. So that's where the high priority go, low priority go. That way I can tease out my time and system for each of those. So when I run my trial, I take this output file that is generated and I copied it and I moved it over to Excel. So I hit this button to copy it and I moved it over to a spreadsheet. I've formatted this a little bit. So for my answers for part 1, the average queue size is about 1.2 people. The waiting percentage, or the probability that a customer will not have to wait, is 25%. The average time in system is this many seconds. Then I'm going to compare, for the second problem, I'm trying to come up with the optimal cost, and I've got economic drivers. So I know how much it costs to add an additional dock, and then I need to use this output to determine what my average queue size is. When you only have one dock and the time between arrivals is exactly the same as the service time. So we have people show up, or we have trucks arriving 5 per day, and the service rate is 5 per day. If that's the case, that system is unstable. Anytime the service rate is equal to or slower than the arrival rate, you're going to have an unstable system. I can say it in terms of times. When the time between arrivals is shorter than the service times, that means people are showing up, but not just shorter, but if they're equal, that is an unstable system. So with one dock, you are unstable. The longer you run the model, the worse the numbers are going to get. You're going to have at least 2 docks to get stable. So you can see with one dock, I got a huge line. With my second dock I add, the line is dropped drastically. And when I add the cost of capacity against the cost of waiting, that gives me a total cost, and this number is clearly less than just adding capacity for a third dock, so 2 docks is the optimal. The maximum, the size of the parking lot I need to calculate that based on the maximum queue size, for 2 docks, because that's my optimal. The max queue size is about 13, so you need to have 13 or 14 docks if you're going to, or parking places if you're going to have a 2 dock operation. And for the last one, that's those numbers. That's just it's not a percent. That's just a number. Sorry. The system utilization is about 67%. And that's not a very high utilization, so that means the system is pretty good and just about everything is going to get through in a reasonable amount of time. However, the low priority, the priority 4 things are in it just a little bit longer because we don't service them first. We service them last if there's anything else in the system. So the time in the system is a little bit more on average than for the high priority systems. Okay, that's enough information, I think. Contact me if you have any other questions. Thanks.